last lecture, I discussed some salient features of L2, the space of square integrable functions. So that's L2 of AB, and this could be minus infinity and B could be infinity. Today I will continue to look at square integrable functions, and I will describe the concept of the wave function psi of x. Introduced it last time as the state psi, which is a ket residing in an abstract Hilbert space, and x is a continuous basis set, could be the position basis, I'll use x for position, and this object is psi of x. So let me quickly recapitulate how we got this. You will recall that any ket psi can be expanded in terms of the basis states phi sub n, normalized basis states phi sub n, with expansion coefficients Cn. And if I normalize psi, it automatically follows that summation over n mod Cn squared is 1. Equally true that I get a particular coefficient Cp as phi p psi inner product, because this is like phi p summation over n Cn phi n, and I use the fact that phi p phi n inner product is delta p n, and therefore I get Cp. So the coefficients along a certain basis are got by doing this. Take that ket which is being expanded in terms of the basis. The bra is really that particular basis state along which you need the coefficient. So in that sense, suppose x is the basis set, x is the basis set, and psi is expanded in the position basis, this object inner product x psi, which is psi of x, which is a scalar and the analog of C sub p. And therefore this is simply an extension of the definition that we had there to a continuous basis, and that's how we got psi of x. And because the basis is a complete basis and a continuous basis, we have this over the range AB. Remember, we are talking of L2 in the range AB, and therefore this is the identity operator. Can always introduce it wherever I want. In that sense, I did this. Suppose I have a state psi which is normalized to 1. I can well introduce this complete basis there, and that would amount to saying integral a to b psi star of x psi of x dx is 1. Because I have introduced a complete set of states, if psi of x is this, it implies that psi star of x is this object, the inner product of bra psi with ket x, and therefore I got that. Now operators themselves have to be written in this basis, even as we did earlier for the 2-level atom, where we had basis states and the operators were formed out of those basis states. Here too operators have to be written in this basis, and therefore the simplest operator that one can think of is the identity operator times x. So let's see how this operator x acts on the position basis. So I'm going to write this as integral dx prime. Let me work in the range minus infinity infinity. This is the identity, and then x is a variable. I can just pull that out. So what happens when let us call this all the same, that is x. So what happens when the operator acts on the position basis? There is this variable x dx prime, and then I have this object, and that is a delta x prime minus x. So the integration goes, and I just have an x. So this is what I have. The operator x acts on the position basis to pull out the number x. And what does it do? Because it is the identity operator, when it acts on the basis set x, it simply pulls out the number x, and that is the same as x. So this object is my position operator. I would simply say that the position operator is represented by x. So I have x pulls out the eigenvalue x, and this is your eigenvalue equation. Of course, the momentum operator p was minus IH cross d by dx. We are looking at one dimensions, the x axis. And in general, the operator p, which is also a vector under rotations in space, is minus IH cross del. And this is where this is the point we got up to last time. Now let us look at the commutator. Now x is Hermitian because it is essentially the identity operator, and I have the commutator x p sub x. I am going to just denote this by p for the moment, is IH cross identity operator, and that is Hermitian. The identity operator is Hermitian. So if you now expand, you have x to be simply replaced by the number x. I am suppressing the fact that there is an identity operator there. So if you wish, we will keep it that way. xp minus px is IH cross identity. Take the Hermitian conjugate. So that is p dagger, x dagger, which is x, minus x dagger, p dagger. And when I take the transpose conjugate in the case of the matrix, all elements get complex conjugated, and therefore I have minus IH cross identity. Now we can compare the two of them. This implies that p is Hermitian, which is the way we want it. We want p to be Hermitian. It is a Hermitian operator because I would like to look at eigenstates of momentum, and the eigenvalues must be real. But p is minus IH cross del in general. We have got p sub x, and therefore it is d by dx. And this is Hermitian. That implies that d by dx is not self-adjoint. By self-adjoint, in this context, I mean Hermitian. So this is a simple way of seeing that d by dx in the case of one dimensions and del in general, the Hermitian conjugate is minus of the operator, and therefore it is not a self-adjoint operator. Now in the case of infinite dimensional spaces, as we will be considering, separable Hilbert spaces, so you have a denumerable infinity of basis states which are orthogonal to each other and normalized to 1. There will be many operators we will come across which are unbounded operators. The position operator is an example. But before going into the properties of an operator in an infinite dimensional Hilbert space, I would like to look at the state psi of x. Psi of x is called the wave function. And the Schrodinger formulation of wave mechanics was about psi of x. In one dimension, the fact that integral psi star of x, psi of x, perhaps the range is a to b, dx is equal to 1 implies that this object mod psi squared has dimensions. That has dimensions 1 by length. This is dimensions length, and therefore mod psi squared has dimensions 1 by length, and therefore psi of x has dimension 1 by root L. This is in one dimension. Now suppose we were doing 2 dimensions, that would have been a d2x, and therefore psi star psi would have dimensions 1 by L squared, and psi of x would have dimensions 1 by L, physical dimensions 1 by L. And if you were working in 3-dimensional space, that would have been a dv, an elementary volume dv, which is dx, dy, dz in Cartesians. And that has dimensions L cubed, and therefore psi star psi would have dimensions 1 by L cubed, and the wave function in 3 dimensions would have dimensions 1 by physical dimensions 1 by L to the 3 by 2, and so on. So this is the way we look at the dimensions of the wave function. Needless to say that a very reasonable physical interpretation can be given to psi of x. We will augment and support our interpretation a little later, but as it stands, recall that in the abstract notation where we expanded psi in terms of the basis states phi n, Cn's were the probability amplitudes, and mod Cn squared was the probability density, and this summation was 1 to tell you that the total probability that that particular physical system represented by the state psi actually exists, and therefore the probability of its existence is 1. Remember, this is number 1 and not the identity operator. In that sense, when we write it in terms of the wave function psi of x, mod psi of x the whole squared is the probability density for the system to be between x and x plus dx. And once the integration is done, psi of x itself would be the probability amplitude, and once the integration is done, it's clear that the total probability is 1. You would expect this because this is the total probability that the system actually exists anywhere between A and B, and if we are talking about a free particle traveling along 1 dimensions, x going from minus infinity to infinity, the probability that the particle exists is given by 1. So this is the probabilistic interpretation of quantum mechanics, which we already knew in terms of the abstract kets in the Hilbert space. And now we are merely working with a basis, a continuous basis in the space L2, and psi of x is the wave function. It is a state written in that basis, expanded in the position basis in this case. Could have expanded it in the momentum basis, but this is an example of how we write a wave function. This is the position space wave function, where x is position. Now let us see how exactly eigenvalue equations look when we write the equation in terms of psi of x and in terms of operators that are expanded or written in the position basis. So we have the energy eigenstates h psi n of x is En psi n of x. In my earlier lectures, where I was not working with the position representation, I had the Hamiltonian acting on psi sub n, giving me En psi sub n. Now H is to be written in the position representation, and these should be made functions of x because we are working in the position basis. The reason why I have used a discrete index n is because I am assuming that the Hilbert space in which I am working out this problem is a separable Hilbert space, and that indeed there is an infinite set of eigenstates, and it is a denumerable infinity, and that is why I use a discrete index n here. So let us look at the simplest example. Let us look at a free particle. There is no potential, and therefore the Hamiltonian gets its contribution purely from the kinetic energy. So I consider a free particle. This is one dimensions. We can always generalize it along the x-axis. So free particle moving along the x-axis, the mass is m and the linear momentum is p. It's clear that the energy operator is p squared by 2m. There is no potential term, otherwise I would have written a v of x. H is an operator and p is an operator, and because we are in the position representation, we are working this in the position representation, and it's a one-dimensional problem, p is minus IH cross d by dx. So we have the equation 1 by 2m or minus h cross squared by 2m d2 psi by dx squared is E psi, where psi is a function of x. This is the eigenvalue equation that one needs to solve in order to find the energy eigenstates. I'd start off by saying d2 psi by dx squared, and then in the case of specific problems, we will be able to see that the energy is quantized, and automatically the quantum number n would appear, E sub n, and corresponding to each of those energies there is a wave function psi sub n, and these would be the energy eigenstates, except that we are now writing them in the position representation or in the position basis. So this tells me that d2 psi of x by dx squared is minus 2me by h cross squared psi of x, and this is a constant. So I define k as square root of 2me by h cross squared, and therefore I have d2 psi by dx squared is minus k squared psi of x. I can solve for this. It's clear that psi of x is e to the minus ikx. That's one solution. There is also another solution which is e to the plus ikx, and therefore in general psi of x is a e to the minus ikx plus b e to the ikx. K is simply a number, and as x changes, psi also changes. A and b are constants, and they are to be determined from boundary conditions on psi. One thing is pretty obvious, that the solution is essentially a harmonic wave. This is simply a fallout of the de Broglie hypothesis, that matter has harmonic waves associated with it. The momentum p would be h cross k, and in general E would be h cross omega, where omega is the angular frequency. So this is the solution to the eigenvalue problem for a free particle moving along the x-axis. I have not put in time dependence yet. I have simply written the eigenvalue problem h psi equals E psi in the position representation and gotten hold of this solution for psi of x with A and B to be determined from boundary conditions. It is a free particle, so I should be able to use boundary conditions. What happens at psi minus infinity and psi plus infinity, that is for x going to plus or minus infinity, what is the value of psi? Now there is a probabilistic interpretation to all this, and since I do require that modulus of psi squared dx is finite, otherwise psi is not even normalizable, I am working in the space L2, which is the space of square integrable functions. This automatically implies therefore that mod psi squared is finite as x goes to plus minus infinity. And the boundary condition that we use is that psi of x goes to 0 as x goes to plus minus infinity. So those would be the boundary conditions for this problem. Clearly, if there is a potential, I will not have a solution of that form. Psi of x would not be of the form a e to the minus ikx plus b e to the ikx. So let us take a simple example. Let us take the harmonic oscillator problem, which we have already worked out in terms of abstract kets. So there the potential V of x is half m omega squared x squared, and therefore the Hamiltonian of an oscillator, the momentum is p, the mass is m, and the angular frequency is omega, is p squared by 2m plus half m omega squared x squared. And therefore in the position basis, this is identical to minus h cross squared by 2m d2 by dx squared plus half m omega squared x squared, where I have substituted p is minus I h cross d by dx. It is therefore amply clear that this formalism of quantum mechanics, where psi is written in the position basis, where you talk of psi as a wave function in the position representation and so on, would involve solutions of differential equations, and in particular second order differential equations, because the kinetic energy term is p squared by 2m. So this is an equivalent formalism. Whatever I had done in the past for the linear harmonic oscillator, using h psi is equal to E psi, writing h in terms of a's and a daggers, where a and a dagger was were linear combinations of x and p, abstract operators. I could give infinite dimensional matrix representations for a and a dagger, upper triangular and lower triangular matrices. But having said that, did not solve it in the position basis, and therefore solved it as a matrix a dagger A acting on a column vector gives me a number multiplying that same column vector. Instead, I could use this equivalent formalism and solve for the differential equation. We shall not attempt to solve the differential equation in detail now. The equation itself is h psi is E psi, where h is given by this and psi is a function of x. But on the other hand, certain points are notable. The potential itself, V of x versus x, is a parabola. It is a symmetric potential, symmetric about x is equal to 0. And therefore, going back to my definition of the parity operator, this is an operator which takes x to minus x. It is a one-dimensional problem. It is a reflection operator which takes x to minus x. And like all operators, PH, P inverse takes it to H prime, which is a new operator. and p psi of x takes it to psi prime of minus x, which is the new state or the new wave function. However, here is a situation where p leaves h invariant, because when x goes to minus x, x squared is unchanged, dx squared, and similarly here x squared is unchanged, and therefore p h p inverse equals h. Now in a context like this, where I have h psi of x is e psi of x, I can write p h p inverse p. It's clear that p inverse p is the identity operator, because p takes x to minus x, therefore all operators which are functions of x to the same operators where x is substituted by minus x, and the wave function psi of x goes to psi of minus x. Now if I did p once more, you see, p inverse would simply take psi of minus x back to psi of x, and therefore p h p inverse p, where I have introduced p inverse p as identity here, psi of x E is a number p psi of x. And therefore I have, but p h p inverse is simply h, so h p psi of x is E p psi of x. I see that if psi of x is an eigenstate of h with eigenvalue E, p psi of x is also an eigenstate of h with the same eigenvalue E. Now, if the eigenvalue E is not degenerate, then it is clear that p psi of x is either plus psi of x or minus psi of x. So for a non-degenerate situation, as happens in the case of the simple harmonic oscillator, p psi of x is psi of minus x, but that is plus or minus psi of x. Only then this equation is satisfied, where E is non-degenerate. And therefore, the eigenstates, the energy eigenstates, will have definite symmetry properties. They will either be odd functions of x or even functions of x. And you will recall that in the ground state we showed that psi of x was a Gaussian function of x, and therefore it's an even function of x, going to 0 as x goes to plus minus infinity, which I would require from my probabilistic interpretation. Here is an odd function of x. As x goes to plus minus infinity, psi of x goes to 0. Like that. Look at this. This is another odd function of x. So x goes between its range minus infinity to infinity. So that's an odd function of x, and in fact this happens to be the wave function psi of x for the first excited state of the simple harmonic oscillator. The second excited state is an even function of x, so psi of minus x is plus psi of x as far as the second excited state is concerned. Third excited state is an odd function of x, and so on, it alternates, and these are states with definite parity. You will also recall that I mentioned in the context of the basis states in L2, mentioned the Hermite polynomials as the basis set, essentially the basis set for the harmonic oscillator problem, the linear harmonic oscillator problem, and in that context we did remark that there was a definite parity they were a set of definite parity states. The basis states were a set of definite parity states. So states which were either odd functions of x or even functions of x. Now let us look at the harmonic oscillator operators. So what is the mean value of x in any state psi? I would normally have written psi x psi. In the case of the oscillator, you will recall that I wrote x as a plus a dagger by root 2 and worked out the calculation by finding out the effect of a on ket psi and so on, and a dagger on ket psi and so on. But instead I could now write the whole thing as functions of x. This, as we said, was simply the identity operator apart from x, and this object I can always introduce a complete set of states. So I can write it as integral dx prime psi x prime x prime. Now that is a complete set of states that I have introduced x, and then once more here I can introduce another complete set of states dx double prime x double prime x double prime psi. It is clear that these are the position eigenstates, and therefore I have the eigenvalue equation as follows. I also therefore know that because of orthonormality, this is how I replace the orthonormality condition, because it is a continuous basis, and therefore substituting things in I find that one of the integrals goes, I replace all x double prime by x prime, and I have minus infinity to infinity dx prime. This is psi star of x prime in our notation. This gave me the delta function, and one of the integrals went, and I have psi of x prime. There was a small matter of x double prime being the eigenvalue, and I could have put it here. The x double prime was replaced by x prime, so I could have put it here, or I could have pulled it out and put it there. This is just a variable, so I could have written it as dx prime x prime psi star of x prime psi of x prime, or I could have put it there, could have put it anywhere. And because the integral is over x prime, I can just write this as integral minus infinity to infinity dx psi star of x x psi of x. This is the expectation value of x in the state psi of x. Now let us look at the harmonic oscillator states. The state psi of x has a definite parity. Perhaps we are looking at the ground state of the oscillator. Then psi of x is an even function of x, and so is psi star of x. In general, it is clear even from the free particle case that psi could be a complex function of x, because it could be a e to the ikx plus b e to the minus ikx. But psi star of x, psi of x, is an even function of x. This is odd in x, and therefore between limits minus infinity to infinity, this integral vanishes. Now let us look at the first excited state of the oscillator. Again, psi of x is an odd function of x, and so is psi star of x. And therefore between them, psi star psi is an even function of x, and there is an x here, and therefore the whole thing vanishes. So it is clear that expectation value of x vanishes in every state of the oscillator. If you recall, this result was established earlier in the abstract ket notation, where we wrote x as a plus a dagger by root 2, and discovered that in the energy basis, energy eigenbasis, which I refer to as ket n, my notation now would be x n is psi n of x. So this is the notation now. Ket n earlier written in the position basis is psi n of x. This is the nth eigenstate of the oscillator. If you wish, it is the n photon state. In the scenario of quantum optics, it is the n photon state written in the position representation. It is a wave function for an n photon state. Whatever it is, an equation like expectation value of x is n a plus a dagger by root 2 n. This turned out to be 0 because a dagger was a raising operator and took n to n plus 1, and I had the fact that all the kets are orthogonal to each other. This got it vanishing, and I see it also shown here using the wave function. So that's exactly the result that I got there in abstract notation, that we had here in abstract notation. So now let's look at expectation value of P. So once more, in the abstract notation, I had n p n was n a minus a dagger, these are all operators, by root 2 I n. And once more, the fact that a lowers n to n minus 1 and a dagger raises n to n plus 1, and the states are orthogonal to each other. In any state, any energy eigenstate of the harmonic oscillator, this was 0. In the notation that we use now, that is when we talk of wave functions, expectation value of P in the state psi is integral psi star of x. I am working out in the position representation, and P is minus I h cross d by dx. I have to be careful where I put it because it is a differential operator and it acts on anything that comes after it. So there is a dx here. Minus I h cross are constants. The fact is, if psi of x is an even function of x, as is the case for the ground state, the second excited state, the fourth excited state of the oscillator and so on, d by dx psi of x is an odd function of x. This was an even function of x, and therefore this is an odd function of x, and that's an even function of x, and totally it vanishes between symmetric limits minus infinity to infinity. On the other hand, if psi of x is an odd function of x, d by dx psi of x is an even function of x. This is an odd function, that's an even function, and the answer follows. So expectation value of P is also 0 in all the states of the harmonic oscillator. So whatever was established in terms of abstract kets is now being established in the position representation. We worked with little L2 when we worked with abstract kets, where in the case of the harmonic oscillator problem, the operators a dagger, etc., were infinite dimensional matrices, and the ket n, for instance, was an infinite component column vector with 1 as one of the entries and all other entries being 0. This is an equivalent formalism, and I am explicitly trying to work out those results in this formalism. Although we will really be taking up dynamics somewhat later, it's still worth remembering that the system could move in time, and time is only a parameter in quantum mechanics, and therefore I should really be writing psi of x t in the one-dimensional case. So that's the same as x psi of t. This is in the position representation. Otherwise, in the abstract, I would just have had psi of t or n of t ket, and in the position representation, I simply take this expansion, this inner product. Now, in general, therefore, I would like to attempt to write an equation for psi of x comma t. Turns out that this is the Schrodinger equation. I use the fact that in general psi of x t, going back to the free particle, is a harmonic wave, and therefore psi of x t would be a cos kx minus omega t plus b sin kx minus omega t. This is if I put in time, and omega is the angular frequency, the momentum p is h cross k and E is h cross omega, and k squared, as I have shown earlier, is 2m E by h cross squared, because E is p squared by 2m. So if I have this solution for psi of xt, it's worth finding out what the differential equation is which is obeyed. What is the differential equation which is obeyed by the wave function? So the differential equation can be got by trying to find out d psi of xt by dt, d2 psi of xt by dt squared, d psi of xt, d2 psi by d psi of xt by dx, and d2 psi of xt by dx squared. We look at the first and second derivatives of space and time and try to come up with an equation. So I have psi is a cos kx minus omega t plus b sin kx minus omega t, and therefore d psi by dt is plus a omega sin kx minus omega t minus b omega cos kx minus omega t. So d2 psi by dt squared is minus a omega squared cos kx minus omega t plus b omega squared sin kx minus omega t minus b omega squared sin kx minus omega t. So this object is the same as minus omega squared psi. This is d2 psi by dt squared. Similarly, I can find d psi by dx and d2 psi by dx squared. Minus ak sin kx minus omega t plus bk cos kx minus omega t, and d2 psi by dx squared is minus ak squared sin cos kx minus omega t minus bk squared sin kx minus omega t, or that's the same as minus k squared psi. So d2 psi by dt squared is omega squared by k squared d2 psi by dx squared. Similarly, I can equate the first derivatives with respect to space and time, and I have d psi by dt is minus omega by k d psi by dx. Perhaps this is a possible equation, but in all these cases there is a problem. The problem is this, that if you compare P is h cross k and E is h cross omega, so if you look at the ratio omega by k, for instance, that is E by P, and that is P squared by 2m P, which is P by 2m. That's like saying that this equation depends upon the value of the momentum. Depending upon what the momentum value is, the equation keeps changing. Now we would like an equation which does not involve specific values of P. Obviously, we need an equation which is all encompassing, and therefore you don't want to see an explicit P dependence in the equation. And indeed, you can get an equation like that, provided you equate the first derivative with respect to time of the wave function with the second derivative with respect to space of the wave function. If you look at d psi by dt, I have a omega sine kx minus omega t minus b omega cos kx minus omega t. And if this has to be equated to that, it's pretty clear that a and b will have to have a certain specific ratio with respect to each other. This is minus k squared psi, d2 psi by dx squared is minus k squared psi. And therefore from this I get, if I have to equate d psi by dt times some coefficient as d2 psi by dx squared times some other coefficient, then I get a by b is minus b by a, which implies that b is IA. And then it follows that psi of xt is e to the I kx minus omega t. Apart from a phase. That is not to say that this is the only solution. K is a specified number. Given the momentum p, I have k, p is equal to h cross k. On the other hand, psi is a function of x given omega, these are the constants, and psi varies with x and varies with time. I in general can have superpositions of this as solutions. In general, the solution is integral a of k e to the I kx minus omega t dk for all values of k. So that's a general superposition, which too is a solution of that equation. That's because the Schrodinger equation is a linear equation. The equation itself, which I have not written down, if you put in these values, you will get I h cross d psi by dt is minus h cross squared by 2m d2 psi by dx squared. That's like saying p squared by 2m psi is E psi, because E is p squared by 2m, or h psi if you wish, and that tells you that the energy operator E psi, and therefore the energy operator is I h cross d by dt. This identification is possible from the Schrodinger equation, because I know that energy is p squared by 2m for the free particle. These are all functions of x and time. This is the Schrodinger equation. For psi of xt. Of course, if you choose not to put in time, which is what we will do for the moment, we will take up dynamics later, it is clear that psi is of the form e to the I kx, or a general superposition a of k e to the I kx, which is what we saw earlier when we looked at the energy equation h psi equals E psi without worrying about the dynamics. These are the plane wave solutions e to the I kx. So you have a component which is cosine and another which is sine, and that is the most general solution. Boundary conditions, psi goes to 0 as x goes to plus minus infinity. In the set of lectures to follow, we will not worry about the time development at all. We will merely use the fact that the plane wave solution is e to the I kx, a e to the I kx plus b e to the minus I kx. In the case of the free particle, we will work out specific problems like the harmonic oscillator, or a particle subjected to other types of potentials like a square well potential, or a particle penetrating a barrier, potential barrier, and so on. So these are all problems which we will study without worrying about time at all. And then later on, in a series of lectures, we will talk about the dynamics of a system, the manner in which the system evolves with time.